What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 10, Section 8, Vectors. Let's do it. So when we use letters to represent vectors, they are typically lowercase, something like U, V, or W. These are very standard, and they're usually written in bold font, so you can tell that it is a vector. But that's basically the gist of it. Done. What are I and J and what do they represent? So I and J are unit vectors, and they basically represent the orientation of a vector. So for example, if I had a vector that went across by 7 and up by 3, so the vector would look something like this, right, in that direction, I would represent it as follows. I'd say, all right, the horizontal distance corresponds with the I, and the vertical distance or the vertical movement corresponds with the J, right? And if I had something going down, by the way, right? So let's say we're going right by 5 and down by 2, that would be something like 5i minus 2j, okay? That's how you do it. Done. When a unit vector is expressed a comma b, which letter is the coefficient of I and j? So it's usually in this order, right? Think about the alphabetical order, H, I, J, right? So A is going to go with the I, and the B is going to go with the J, like so. Given a vector with an initial point of -4, 2, and a terminal point of 3, -3, find an equivalent vector whose initial point is 0, 0. Write the vector in component form. So we're starting at -4, 2, and then we're going to 3, -3. And I'm writing it like this because this somewhat indicates the direction, right? We're going from right to left, and we're also going down, right? We're starting at 2, going down to -3. So really what we're looking at is like, what's the distance we're traveling? So we're going across from -4 to 3. So we're going across by +7. And then we're going down, right? We're going from 2 to -3. That's going down by 5. That's indicated by -5. So the component form, therefore, would be 7, -5. Those movements from 0, 0. That's how you do it. Done. Determine whether the two vectors u and v are equal, and u has an initial point at P1, terminal point at P2. V has an initial point at P3, terminal point at P4. So we're going from here to here, and this one we're going from here to here. So really what we're going to do is we're going to try and get the component form of each, and we're going to see if they're the same. So let's look at P1 to P2. It's going a distance of -2, right? We're subtracting 2 to go from 5 to 3. What about 1 to -2? We're subtracting 3 there. So there's our component form. What about P3 to P4? From -1 to 9, it looks like we're adding 10, and then from 3 to -4, we're subtracting 7. So these are definitely different. They're not the same. So we'll say not equal. Done. So for this one, we're going to get the component form first, going from P1 to P2. So what is the change in the x? It looks like it's going down by 3 for the horizontal component, and then -1 to 5, that's going up by 6. What about P3 to P4, right? We're going from -10 to -13, that's down by -3, and then 6 to 12, we're going up by +6. Well, look at that. These two are the same, therefore, these are equal. Done. So for this one, we're going to get the component form of each vector, looking at the change, right, from the first to the second. So from 8 to 6, we're going down by 2. 3 to 5, we're going up by 2. What about P3 to P4? So from 11 to 9, we're going down by 2. From 8 to 10, we're going up by 2, +2. But look at that. These are the same. Therefore, the two are equal. Done. So this one, we want to write this vector in terms of I and J. And first, I'm going to put it in component form, and then I'm going to put it in terms of I and J. So 6 to -1, that looks like a drop of -7. And then 0 to -3, that's a drop of 3, aka -3. Now to put it in terms of I and J, the first number pairs with the I, the horizontal movement. The second number pairs with the J, the vertical movement. And that's how you do it. So for this one, it says use this vector and this vector and this vector to find this. So 4v plus 2u. So what am I really doing? I'm going to plug these in, right? For what is v? It's -2i minus 3j, just like variables, right? We treat I and j just like variables, plus 2 times u. So I'm going to sub that in. That's 1i plus 5j. And just like a typical algebraic problem, what are we going to do? We're going to distribute, right? Boom, boom, and boom, boom. And we got -8i minus 12j plus 2i plus 10j. And then we're going to combine like terms here and here. -8i plus 2i is -6i. -12j plus 10j is negative 2j. And that is how you do it. Done. For the following exercises, use the given vectors to compute u plus v, u minus v, and 2u minus 3v. So this is pretty cool because when we add vectors, it's like you add these two together, almost like in the I position, and then you add these two together in the j position, right? So it's relatively straightforward. So to get the sum, first, u plus v, we'll do it in this order. Negative 3 plus negative 2 is negative 5. 4 plus 1 is 5. So we're going to keep that in component form. When I do the difference, it's negative 3 minus negative 2. That double negative makes it a plus 2. So negative 3 plus 2 is negative 1. And then 4 minus 1, each one is subtracting, right? 4 minus 1 is 3. That's the difference. And then last but not least, 2u minus 3v. So just like if we had a binomial and we're multiplying it by 2, we distribute. So that becomes negative 6, that becomes positive 8. And then when we multiply the second one by 3, that becomes negative 6, that becomes positive 3. And then, of course, we're subtracting. So negative 6 minus negative 6, that's 0. And then 8 minus 3, that's 5. So these are the three answers. Done. Let v equal 5i plus 2j. Find a vector that is twice the length and points in the opposite direction as v. So basically what we recognize is that this is the horizontal distance, this is the vertical distance or vertical movement, right? So if I want this to be double the length, I can just double each of those components. So I can make it 10i and 4j. But I want it going in the opposite direction, right? So instead of going to the right by 10, I'm going to go to the left, aka make it negative. What about the 4? Instead of going up by 4, I'm going to go down by 4. So this is how you do it. Done. So for this one, we want a unit vector in the exact same direction as this. So how do we get a unit vector? So the way we do it is we kind of take what we have and we have to divide each of these values by the magnitude. And by the way, what is a unit vector? A unit vector is literally a vector with a magnitude of 1. Okay, so let's go through the process. First of all, what is the magnitude of this vector, right? We take this first component, negative 2, and we square it. We take the second component, 5, and we square that. And we take the square root of this, right? So it kind of looks like the distance formula. Negative 2 squared is 4. 5 squared is 25, and the square root of that is 29, square root of 29, right? Then we take each of these individual components and we divide them by the magnitude. So we get negative 2 over rad 29i plus 5 over rad 29j. And that is how you find the unit vector. Done. So for this one, we first have to find the magnitude of this vector in order to get the unit vector. So to get the magnitude, we take the square root of this first value, that first coefficient, negative 1/3 squared, plus the second one squared, right? 5 over 2 squared. All right, let's simplify that. So this is 1/9 plus 25 over 4. To get common denominators, let's go with 36. So we got 4 over 36 plus 9 times 25, that's 225 over 36, like so. Add those together, 4 plus 225 is 229 square root over the square root of 36. But the square root of 36 is 6, so we can simplify that. All right, so there's that. Now we take these values and we divide them each by this, which is the same as multiplying by the reciprocal. So we've got negative 1/3 times the reciprocal of this, which is 6 over rad 229, and then plus 5 over 2 times 6 over rad 229, and don't forget the I and the J, like so. All right, now let's simplify it a little bit, and they did rationalize the denominator in the answer choice, so we're going to do the same first. Let's simplify. This simplifies to 1 and 2. This simplifies to 1 and 3. So then we got negative 2i over rad 229 plus 5 times 3 is 15 over rad 229 times j. And then last but not least, to rationalize the denominators, multiply the top and bottom by rad 229. We'll put the answer up here. So then on top, we got negative 2 rad 229 over 229, right? Because radical times itself is just a number. And we got the I. And then it's plus 15 rad 229 over 229 times j, like so. And that is how you do it. Done. So for this one to turn it into unit vectors, first I need to get the magnitude, which can be found by taking the square root of this value squared plus that squared. So negative 14 squared, that's 196, right? And then 2 squared is 4. So we got radical 200. We can simplify that a little bit because you remember that's the same as 2 times 100. Square root of 100 is 10. So we got a nice magnitude of 10 rad 2. And then we divide each of these components by 10 rad 2. So it's negative 14 over 10 rad 2i plus 2 over 10 rad 2j. And we're going to rationalize the denominator. So I'm going to multiply the top and bottom by rad 2 and rad 2. So then we get negative 14 rad 2 over 10. And then rad 2 times rad 2 is 2. And then we got the I plus 2 rad 2 over 10. And then rad 2 times rad 2 is again 2j. And then we can cancel those, right? 2 over 2. And then 2, and that divided by 2 is 7. So final answer is negative 7 rad 2 over 10i plus rad 2 over 10j. That's how you do it. Boom, done. So for this one, to find the magnitude, what you do is first you take the square root of each of these pieces squared, added up. So it's 6 squared plus 5 squared. And that's going to give you 36 plus 25, which is rad 61. And rad 61 is approximately 7.810 to the nearest thousandth. So magnitude of this vector v is 7.810. Now, we're trying to find the theta value. The formula for that is arc tangent of the second piece, the y piece, if you will, over the x piece. 5 over 6. Let's see that in Desmos. Now we're going to put in degrees. And we get 39.806 degrees rounded to the nearest thousandth. So theta equals 39.806 degrees. That is how you do it. Boom, done. So for this one, first we're going to get the magnitude by taking the square root of this value squared plus this value squared. So that's negative 4 squared is 16, negative 6 squared is 36. Add those together and we get radical of 52. And we're going to see what that is, approximates to in Desmos. Square root of 52 is 7.211. So 7.211 for the magnitude. Now, what about the theta value? Again, theta is going to be arc tangent of the second value over the first value. So positive 6/4. And we get 56.3. Now, the thing is that when we go back here, remember, these were both negative. So what that means is we're really going left and down, which means we're actually going this way. So if we think about our starting position here, if this is like 0 degrees, right? We're actually coming all the way around. So it doesn't make sense, like the angle that we originally got would probably be going up like this. So we need to get that same reference angle, but in the third quadrant, not the first quadrant. So the way we do that is we take this angle and we just add it to 180. Boom, like so. And we get 236.310 when we round up to the nearest thousandth. So theta is 236.310. Those are the two solutions. That's in degrees, by the way. There's the magnitude, done. Here we're doing a dot product, and what you do with the dot product is kind of like the terms that are linked up, right? The two I value coefficients are going to multiply, so that's -1 coefficient times +1, and then the two j coefficients, that's -1 and 5. Those are all multiplied, and then the product of each of these are then added together. So we got -1 plus -5, which gives -6 for the dot product. Boom, done. For this one, to get the dot product, what we're doing is we're taking these two components in the first position, multiplying them, the two components in the second position, multiplying them, and then adding those products together. So -1 times 6 is -6. 6 times -1 is -6. Adding these together, we get a dot product of -12. That's how you do it, done. So for this one, we're meant to draw V, which is this, 3 times V and 1/2 times V. So let's first get those two out here as well. So if we have 3 times V, we multiply each piece by 3, so we got -3, 12. And then 1/2, we multiply each 1 times 1/2, like a distributive property, so we get -1/2, 2. All right, let's plot these out. So the way you want to think about all of these is, first of all, they're all starting at the origin, and then this is the direction left, this is the direction up. So we go left 1, up 4. So boom, there's my vector there. For this one, we've got -3, 12. So we go left 3, up 12, like so. And again, starting at the origin, so that's that one. Last but not least, -1, half 2. We go left a half, up 2, and there's that vector. That's how you do it, done. So for this one, we're meant to draw u plus v, u minus v, and 2u based on this original diagram. So let's start with 2u because that's going to be the easiest. So if this is u right here, right? So it's currently just going across like this. To do 2u, I'm literally just doubling it straight up. So it's going up 1 over 1, now it's going up 2 over 2. So what about u plus v? So first let's draw our original u and our original v like so. So the cool thing about vector addition is what you can do is you can take the starting point and you can add them together by doing head to tail. So I kind of move that v like this. And then look where it is. We have a starting point here and an ending point here. Now that I know that, I can draw the vector straight up connecting the starting and the ending points. And there's my u plus v, just move those two, and that's how you do it. What about u minus v? So the way to think about u minus v is it's really v negated being added to u. And if you negate u, it just literally goes like that in the opposite direction. So if we, once again, if we start with u going up like this, and then we do the same idea, we add head to tail. So I'm going to take this one that I made over here, and I'm going to drag it, I'm going to go boom like this. Head to tail once again. And now we can see what this vector is. We got a starting position here. We got an ending position here. Now we connect the dots. And there's u minus v. We'll just get rid of the original u and the original negative v. And there it is. Those are the three answers. Done. So for this one, we're going to color code it. And I'm going to show you how to do u plus v, u minus v, and 2u in these different colors. So first of all, when I add u plus v, I do it from head to tail. Well, it kind of already did that. Look, we can already see u here and v, and they're already head to tail, which means u plus v, is just the starting point of u going to the ending point of v. Now for u minus v, again, it's u plus negative v. Well, since v is going in that direction right now, negative v would be going up here. So now we have the starting and ending point for u minus v, which means we can just connect those across right there. And you can see in purple, and I'll remove this, there is u minus v. Now we come to the last one, 2u. And the cool thing about 2u is we take our existing u and just double it. So it was going down 2 over 3. Now it's going down 4 over 6. So that's how you do it. Done. So for this one, we're doing 2u plus v. And the way we're going to do it is we're going to first find 2u, which we can do by just taking the existing u and doubling it. So there's 2u, and then what we're going to do is we're going to add v to it, again, going from head to tail. So here's v, and I'm going to move it down head to tail like so. And then now we get our nice starting point here and an ending point here. Now we connect the dots, and there we go. You see we go down 6 to the left by 1. That's how you do it. Done. So this one is u minus 3v. The first thing I'm going to do is find negative 3v. So we know that when we negate it, we're going in the opposite direction, but then we're also tripling it. So 1, 2, 3, like that. So now I've tripled it in length. And then if we're adding it to u, I do that head to tail thing, but we don't really have enough room where it's positioned here on this graph. So I'm going to redraw u like that, right? Up 2 over 1. And then I'm going to move this guy like here. And then we have a starting point here and ending point here. And our final vector comes across like so. And there's the final vector. Done. For this one, we're meant to put it in component form. And I see it's going up 1 and over by 4. So putting the horizontal move first, it's 4, 1 for the vertical. That's how you do it. Done. Given the initial point 4, -1 and terminal point -3, 2, write the vector in terms of I and j. All right, so let's think about this for a second. We're starting at 4, -1, like, and just this is just approximate, right? 4, -1, and then we're going left and up to -3, right? 2. And so when we think about the vector in terms of I and j, right, the I coefficient is going to be how much we're going across, and the j coefficient is how much we're going up. So how much are we going to the left? We're going from 4 to -3, so that's -7. We're going from -1 to 2, that's up 3. So then we have -7i plus, because that's positive, 3j. And just so you can see what this would look like on a graph, we got 4, -1, right? And then we have -3, +2, like so. And that would be the graph of the vector. Boom, done. So for this one, we want to get this into component form, and we need to find the x and y components, and we use this formula to do so. So x equals the magnitude, which is 6 times cosine of 45, and same for the y part, it's 6, but instead of cosine, it's sine of 45. So let's use the unit circle to calculate this. And the cool thing about cosine and sine of 45 is they're both the same thing. They're both rad 2 over 2. So it becomes 6 times rad 2 over 2. 6 times rad 2 over 2 simplifies to 3 and 1, right? Divide them both by 2, 3 and 1. And now to put this into component form, it's the first value 3 rad 2i, and then the second value plus 3 rad 2j. There's component form done. So for this one, to get the corresponding x and y values for component form, we first get x by taking the magnitude times cosine of that angle 300. And the y part is the same thing, magnitude, except it's times sine of that angle. And this is an angle in the unit circle. If you remember, it's all the way here with a nice reference angle of 60 degrees. So we can now figure this out. So cosine of 60 is actually 1/2, and in quadrant 4, it's still positive. So it's gonna be 1/2 times 2, so that's x is 1. And then sine of 300, or sine of 60, that's going to be rad 3 over 2. And since we're in quadrant 4, that's negative rad 3 over 2. So negative rad 3 over 2 times 2 is negative rad 3. So now we get it in component form. This goes with the I, so it's 1i, or just I, minus rad 3 times j. That's how you do it. Done. A 60-pound box is resting on a ramp that is inclined at 12 degrees. Find the magnitude of the normal perpendicular component of the force. So before we do that, let me draw out a little diagram. So we're talking about a ramp that, if we look straight at the ground, has an incline of 12 degrees. And then we have a box that is resting here that is 60 pounds. So if we find the vector going perpendicular to this, that would be at 90 degrees to that, going like this. And then we can get the full angle 90 plus 12, which is 102 degrees. So now to get our final answer, we do that weight 60 times sine of that angle, which is 102. Let's see that in Desmos. And the answer rounded to the nearest tenth is 58.7. Part A is 58.7. Okay, now part B. Find the magnitude of the component of the force that is parallel to the ramp. So that's basically with our original angle. So now we're going to take 60 sine of just 12. Let's plug that into Desmos. And here we get 12.5 to the nearest tenth. So for part B, 12.5 is the answer. Boom, done. Find the magnitude of the horizontal and vertical components of a vector with magnitude of 8 pounds pointed in a direction of 27 above the horizontal, round to the nearest hundredth. So as we draw this out, we got this angle of 27 degrees. And we need the horizontal and vertical components. So the way we're going to get the horizontal components is that 8 pounds times cosine of that angle, which is 27. And to get the vertical component, it's 8 times sine of 27. So let's get both these values now approximated. So 8 cosine is 7.12. 7.12 is the x component, the horizontal component. And then for 8 sine of 27, we get 3.63. So the y part is 3.63. That's how you do it. Done. Find the magnitude of the horizontal and vertical components of a vector with magnitude 5 pounds pointed in a direction of 55 degrees above the horizontal, round to the nearest hundredth. So the x component is going to be the magnitude times cosine of that angle, and the y piece is going to be the magnitude times sine of that same angle. So let's check that now in Desmos for both of these. So for cosine, it's going to be 2.87 to the nearest hundredth. This one's going to be 4.10, right? It's going to round up to the nearest hundredth. So we got 2.87 and 4.10. That's how you do it. Done. A woman leaves home and walks 3 miles west and 2 miles southwest. So 3 miles west and then 2 miles southwest. So south and left, so kind of like this diagonal, and that would be 2. How far from home is she, and in what direction must she walk to head directly home? So to figure this out, let's look at the full vector from the beginning, head to tail, right? So now to figure out how far she is, we need to calculate the length of this. And this might look familiar, right? This is a triangle, but it's not a right triangle, right? It's a triangle with 3, 2, and we need to figure out this long length. And we can do that. We just need some angles in the mix, right? So if we think about it like this is going straight across, and then this is going exactly southwest. That means this is going at an exact 45-degree angle, which means if this is going straight down, if it was going like this, that'd be 90, but then it's going another 45. So 90 plus 45 is 135. So guess what? We have enough for a little law of cosines, right? If this is x, we can set it up like this. We can say the unknown side x squared equals the known side 2 squared, which is 4, plus 3 squared, which is 9, minus 2 times the known sides 2 and 3 times cosine of that angle opposite x, which is 135. This gives us enough to solve that distance for x. And by the way, to do this, we can use Desmos, but remember, we're gonna have to take the square root of both sides, so let's do that now. And we get 4.635 miles. And then now we need to know the direction to head back home, right? So we're here and we need to go back this way. So what is that direction? So if we say that this would be going directly east, we need to know what angle from going directly east, meaning how many degrees north do we have to travel from going straight east to be in that right direction, right? So what is this angle? And the cool thing about this angle is it's the same as this angle because this is parallel to this, right? Those are alternate interior angles. So how do we figure out this angle? Well, we can use a little law of sines, okay? So check this out. I can say sine of this unknown angle, I'll call it A, over the opposite side 2 equals sine of 135, right, over its opposite side, which we now calculated as 4.635. Okay, cool. We're going to multiply the 2 across, and we get sine of A equals 2 times all of this, which I'll calculate in Desmos. And so when you plug it into Desmos, we get 0.305. So then sine of A equals 0.305. To solve for this, we have to take arcsine of both sides. So A equals arcsine of that, which is approximately 17.765. So what we'll say is the bearing is 17.765 degrees north of going directly east. So those are the two answers. Boom, done. A man starts walking from home and walks 4 miles east, 2 miles southeast, 5 miles south, 4 miles southwest, and 2 miles east. How far has he walked? And if he walks straight home, how far would he have to walk? So first, let's plot this out as it's being described. So we're going to try and do this somewhat to scale. So we're saying 4 miles east, that's directly to the right, 2 miles southeast, so it would be right at that nice 45-degree angle. Then 5 miles straight south, so we're going straight down. Then 4 miles southwest, so that's coming back like so, 4 miles southwest. And then finally 2 miles east like so. So for the total distance that's walked right now, we just add these up. 4 plus 2 is 6, plus 5 is 11, plus 4 is 15, plus 2 is 17 miles. And how far would he have to walk if he went on a straight path from here all the way up? And I'm going to put that in red. So the way that I'm going to go about this is I think we have enough information to actually make a triangle like so, that is a right triangle. And we're going to try and figure out the vertical and horizontal distance. The reason why I can do this is because all of these are nice, perfect, like 45-degree angles, right? So I can figure some things out nicely. For example, if I'm going at a 45, 45, 90 with this little vector here, I can figure out that this vertical distance right here is going to be 2 divided by rad 2. That's just from my knowledge of special right triangles, right? 2 divided by rad 2 is rad 2. And that's also going to be rad 2. And that makes sense because to go back from the smallest side to the hypotenuse, I multiply by rad 2, and I do indeed get 2. Likewise, this is another nice little 45, 45, 90, which means 4 divided by rad 2 gives a side length of 2 rad 2 here, as well as here, 2 rad 2. Now I have enough information to find the length of this blue side, because I'm going to add up rad 2, 5, and 2 rad 2, which gives me 5 plus 3 rad 2. And for the green side, it's a little bit trickier, but I'm going to the right by 4, and then I'm going again to the right by rad 2, and then I'm going backwards, right, this distance, by 2 rad 2, so then I'm minusing 2 rad 2, but then I'm kind of starting here, and then I'm going back again this distance of 2, so I'm adding 2 again. So then I got 6 minus rad 2. And this is great because this is a right triangle, and I can use Pythagorean's theorem now, right? So I can say a squared, which is 5 plus 3 rad 2 squared, plus b squared equals the hypotenuse squared, right? But I don't want the hypotenuse squared, I want the hypotenuse. So if I take the square root of both sides of that equation, or basically of this expression, I get the length of the hypotenuse. Let's plug it into Desmos now. And we get 10.318 rounded to the nearest thousandth. So the answer would be 10.318 miles if we walk back straight. So that's the answer there. Here's the original answer. Boom, done. A man starts walking from home and walks 3 miles at 20 degrees north of west, 5 miles at 10 degrees west of south, and then 4 miles at 15 degrees north of east. If he walked straight home, how far would he have to walk? Would he have to walk, and in what direction? So first we got 3 miles north of west. So here would be going straight west, and 20 degrees north would be angled up like this. Then we go 5 miles, 10 degrees west of south. So if here we're going south, then we'd go 10 degrees west would be like this. And then we got 4 miles at 15 degrees north of east. So if here's east, we got 15 degrees north like so. So now the question is, if he walked home, how far would he have to walk and in what direction? So that'd be the red vector. So to get the vertical distance and the horizontal distance for this one coming across, I'm going to use that magnitude 3 and that angle of 20. And again, really that angle coming across here is 20 north of west, which is really the same as 160 degrees. So the horizontal distance, is 3 cosine of 160, and the vertical is 3 sine of 160. So for now, we'll just put 3 sine 160, and then coming across 3 cosine 160. And then over here, the amount going like this and like this, we have to do these calculations again. So here we have an angle coming that is 10 degrees west of south. So south will be coming straight down like 270 degrees. 10 degrees west would be a little less, 260. So again, now we have that magnitude 5 cosine of 260, and then coming down is 5 sine of 260. And then last but not least, we have coming across this way the magnitude of 4. So we're going like this and like this. And that angle is 15 degrees north of east. That's just straight up 15. So we got 4 cosine of 15 for sine of 15. So now we can start to build a little triangle here, and we just have to calculate the purple and the green length of that triangle. So to get that purple length, we take this entire vertical distance, and then we minus this distance and this distance right here. And then to get this green distance in here, it's this full horizontal distance minus this distance and this distance right there, like that. And these are now going to be the A and B values for Pythagorean's theorem. So if I take these values, I square them, and I add them together, take the square root, right, using Pythagorean's theorem, we're going to get an answer for the distance. So let's do that now in Desmos. So once you plug it all in, these are the values. That's A, that's B. We need those both squared. So we square them each, add them together, and then we take the square root, and there's our distance, 2.868. So 2.868 miles. And now we want to know the direction. And so the way they did it is they wanted to know the angle north of west. So west would be coming straight across like this. So we're talking about this angle in here, which is basically a complement to this angle in here. So to get this inside angle, I can take inverse tan. I know we got a lot going on here, but I can take inverse tan of the opposite side over the adjacent side, which is, that opposite side, which is the green value, over the adjacent side, which is the purple value. We got that in Desmos. Let's calculate that. So there's the opposite side. I just did a little copy and paste, and there's the adjacent side. And we get this tiny little angle, but again, we need the complement of this, which is this subtracted from 90, and there we go, 86.474. So we say 86.474 degrees north of west, and that's how you do it. Done. An airplane is heading north at an airspeed of 600 kilometers per hour, but there is a wind blowing from the southwest at 80 kilometers per hour. How many degrees off course will the plane end up flying, and what is the plane's speed relative to the ground? So at this point, we're going to draw this out. So first, I'm going exactly north at an airspeed of 600. So that's going to be going directly up. So now this is saying that we've got something flying from the southwest, right? A wind blowing from the southwest. So if it's coming from the southwest, it's going northeast, right? It's going in that direction with a nice 45-degree angle. So I'm going to take this and add it up here. Okay, now this is not perfectly to scale, but this is meant to represent 80 kilometers per hour. This is representing 600. Now we're going to draw the vector that results from those two kind of combined, and it's like that. And to figure out the new speed, we have to figure out the magnitude of this vector, and we also have to figure out this little angle in here, right? That's the direction. And before we do that, we need to know what this angle is. Luckily, I do know what this angle is, because coming straight out like this would form a 90-degree angle, and then again, it's at a kind of like an exact 45-degree angle. So it's 90 plus 45, which is 135. And now we have enough to use law of cosines. So if I call this opposite side x, we can say x squared equals 600 squared, one of the sides, plus 80 squared, the other side, minus 2 times one side, 600, times the other side, 80. And then it's times cosine of the angle opposite the unknown, which is 135. So we got it set up like this. And I don't want x squared, I want x. So of course I'm gonna have to take the square root of both sides like so. And let's plug that into Desmos now. And we get approximately 659, so that's the speed. And now we wanna get this little angle in here. And what we can do now is actually we can use a little law of sines, right? So I have an angle, I have an opposite side, I have an unknown angle and an opposite side. So let's set it up. So we got sine of 135 over the opposite side, 659, equal to sine of my unknown angle, let's call that angle A, I guess, and then sine of A over the opposite side, which is 80. Okay, let's cross multiply, boom, boom. We get 80 sine of 135 equal to 659 sine of A, right? I'm gonna divide both sides by 659. So we got, let's do it over here, 80 sine 135 over 659, and that equals sine of A. So to get just A, I need to take arc sine, the opposite of sine of this. I hope you can see that. Let's plug that into Desmos now. And we get 4.924 degrees. So it's off course by 4.924 degrees, because it should be going straight north, but it's going that way. So that's the angle that it's off. That's the ground speed. Boom, done. An airplane needs to head due north, but there is a wind blowing from the southwest at 60 kilometers per hour. The plane flies with an airspeed of 550 kilometers per hour. To end up flying due north, how many degrees west of north will the pilot need to fly the plane? So the way we want to map this out is first we've got a wind coming from the southwest, right? Southwest. So that means it's kind of going northeast. And then we've also got a vector that's going 550 miles per hour. That's the velocity. But we need to angle it at a certain angle such that when we position it at the right angle, the resultant vector is going to be going exactly due north, right? So exactly straight. So again, we got 550 here, and then we've got 60 here. And the cool thing is I do know this angle because this is coming, like I said, exactly northeast. So this angle in here is 45 degrees. So that's helpful. So then to figure this out, we need to figure out how many degrees west of north. So this would be going straight north. So we need west of north. So it's like this little angle is what we eventually need to solve for. And the good thing about that angle is it's the same as this angle, right? They're alternate interior angles. So this is terrific because I already have enough information to use law of sines, right? I've got this angle that is unknown. We'll call it x. And I can say sine of x over its opposite side, which is 60, right, is equal to sine of 45 over its opposite side length, which is 550. Look at that. We got it all set up. Now we're going to cross multiply and solve. So we got 60 sine 45 equals 550 sine of x. Divide both sides by 550. Sine of x equals 60 sine 45 over 550. Last but not least, I need to take arc sine of both sides. So I'm going to take arc sine. That's going to just cancel out the sign there. And then arc sine of this quantity, which is 60 sine 45, 550. Let's plug it into Desmos. And we get 4.424. So the answer is 4.424 degrees west of north. Boom, done. As part of a video game, the point 57 is rotated counterclockwise about the origin through an angle of 35 degrees. Find the new coordinates of this point. So let's do that now. So here is 57 right here. And they said it's rotated counterclockwise. That's going this direction, right? So we got through an angle of 35 degrees. So just to kind of make an approximation, we're going to say 35 degrees. Let's say it looks like roughly like this. And we want to know the new coordinates of this point. Now, since these are going to have the same magnitudes, let me calculate the magnitude of this line. And I can do that because I've got 5 out, 7 up. So the magnitude is the square root of 5 squared, which is 25, plus 7 squared, which is 49. And that's the square root of 74. So this is also going to have a magnitude of the square root of 74. But it's rotated 35. So the question is, what is this entire angle? Because if I know that, I can get the corresponding x and y values using a nice little formula, which I'll get to in a second. But how can we figure that out? Well, first, what is this angle in here? I can figure out that angle by taking arc tangent of the original coordinate, the y value over the x value, aka 7/5. Let's see that in Desmos now. So we got an angle of 54.462, and then we're going to this new point in additional 35 degrees. So I add that to 54 and I get 89.462. And now I can use my nice little formula, which is that the x value equals that magnitude, rad 74, times cosine of that final angle, 89.462. And then the y value equals the same thing, the magnitude, rad 74, times sine of that same angle. So let's plug those into Desmos now. And for the x value, we get 0.081 rounded to the nearest thousandth. And here we get 8.602. So the final coordinate is 0.081, 8.602 rounded to the nearest thousandth. That's how you do it. Done. Two children are throwing a ball back and forth straight across the back seat of a car. The ball is being thrown 10 miles per hour relative to the car, and the car is traveling 25 miles per hour down the road. If one child doesn't catch the ball and it flies out the window, in what direction does the ball fly, ignoring wind resistance? So what this sounds like to me is, let's say we're going this way at 25 miles per hour, and then we're going directly perpendicular, because it says going back and forth, right? Left to right, I assume, at 10 miles per hour, meaning that forms an exact right angle. So we want to know what direction this thing is going to go out the window if it kind of continues out, and that's going to be this resultant vector here. So what we're looking for is this little angle, and this is great. This is all we need, because if you think about it, right, remember that angle, let's call it x. I can say tangent of x is equal to opposite over adjacent. So I just have to take arctangent to get that angle. Arctangent of 10 over 25, right? The opposite of taking tangent. Let's see that in Desmos. And we get 21.801 degrees. So 21.801 degrees relative to the car's forward motion. Done. A 50-pound object rests on a ramp that is inclined 19 degrees. Find the magnitude of the components of the force parallel to and perpendicular to the ramp to the nearest tenth of a pound. So first of all, here's the ramp at 19 degrees incline, and then normal or perpendicular to the ramp then would be a full angle of 90 plus 19, which is 109 degrees. And since the item has 50 pounds, now we can sort of use our formula to calculate the magnitude. So what we're gonna do is we're gonna take the weight times sine of 19. That'll give us the one that's parallel first. That'll give us the first value. And here we get to the nearest hundredth, 16.28. So there we go for parallel. And then for perpendicular, we do the same thing, 50 times sine, but instead of 19, we use that second angle we found, which is 109. And we get 47.28 to the nearest hundredth. And those are the answers. That's how you do it. Done. Suppose a body has a force of 10 pounds acting on it to the right, 25 pounds acting on it from negative 135 degrees from the horizontal, and 5 pounds acting on it directed 150 degrees from the horizontal. What single force is the resultant force acting on the body? So let's draw this out first. So we got 10 pounds of force going to the right. Then we've got 25 pounds acting on it, negative 135 from the horizontal. So here's the horizontal. Negative means we go this direction. So here's 90. Here's another 45, like so, and that's 25. And then we have 5 pounds acting on it, 150 from the horizontal. So we say here's the horizontal, and then 150 would be 90, and then another 60, like so. So then we go to the starting point, out to the ending point, and that's sort of the resultant vector. So the way we can figure this out is by making a little makeshift triangle here, like so, and let's make that a nice 90-degree angle. So we need to figure out this value, and we need to figure out this value, aka the width and the height, right? So the way we can do this is we can think about going like this, right? We've gone 10 exactly to the right, then we're going backwards this way. So we have to figure out what is this kind of horizontal distance that we've gone back to the left. So if I look at this as a triangle, I can see that this angle in here, right? We already said this in here is 45. So this is also 45. So I can figure out this horizontal distance by using my formula magnitude 25 times cosine of this inside angle of 45. And then we're going again back to the left. So we again make this into a little triangle. We need to figure out this distance. And since this angle is 150, this little angle in here is going to be 30. So we're again going a little bit further to the left, minusing the magnitude 5 times again cosine of 30. So this is going to give me this distance in here, right? I'm doing 10 minus this distance minus this distance. So it's going to be a negative value. Obviously, we're talking about a triangle. We're talking about distance. So we're going to take the absolute value. Okay, then let's talk about this vertical value going from here to here. And what that is this vertical value up and down, which I can get from doing magnitude 25 sine, for vertical, 25 magnitude times sine of that angle, and then minus this distance, which is magnitude again times sine of 30. And then once I get these values, I can use Pythagorean's theorem to get that magnitude, right? I can say a squared plus b squared equals c squared, so I have to take the square root of that. So, you know, this is my a squared value. This is my b squared, or a value and b value. And I have to square them, add them together, take the square root. Let's do that in Desmos now. So here are the two lengths, 12 and 15 approximately. Now we're going to square each and add them together and then take the square root. And rounded to the nearest hundredth, we get a magnitude of 19.35. So that's 19.35 pounds. And then we need to get the angle. So how can we figure out this angle in here? Well, we can do a cool thing. We can take, if I call this side A and I call this B, right? We can take arc tangent of B over A, right? Opposite over adjacent. And again, remember, this is the B value down here, right? And this is the A value. So we already got them in Desmos. Let's check it out. So there it is. Arctangent of opposite over adjacent is 51.65, but that's just this angle. We need the full angle from horizontal. So to get that, I have to add 180 to this value, which gives us 231.65 degrees. Slightly, just the tiniest bit different from the back of the book, but that's the general protocol. So we'll say 231.65 degrees from horizontal. I'll say like this, as shorthand. So that is how you do it. Done. Suppose a body has a force of 3 pounds acting on it to the left, 4 pounds acting on it upwards, and 2 pounds acting on it 30 degrees from the horizontal. What single force is needed to produce a state of equilibrium on the body? So let's draw this out. So we got 3 pounds acting on it to the left, then we got 4 pounds acting on it upwards, and then 2 pounds acting on it 30 degrees from the horizontal. So here's the horizontal and 30 degrees up like so. So that's kind of like what's happening, right? It's ending up over here. So what they're saying is, what single force to get it to a state of equilibrium, meaning we need a vector firing it right back in the opposite direction of that resultant vector. So essentially, it's just like finding the magnitude of the red and then this kind of like reverse angle, like not this angle, but you know, whatever this one would be, like negated basically. So again, we're going to take that same strategy of making like a little triangle here. And to first get this distance right here, we know we're going 3 that way. So it's like 3, and then we're minusing whatever this distance is right here. And since I know this angle in here is 30, I know that this angle up here is 30 as well. So I can use that to calculate that horizontal distance, because I can say that's the magnitude of 2 times cosine of that angle 30. So that's going to give me that horizontal portion. And then to get the vertical portion, I see that we're going up 4, and then I need to add this portion right here, which is 2 sine of 30. And now we're going to do Pythagorean's theorem, and we're going to say this squared plus this squared and take the square root of the sum of that. So here are the two values, and then squaring each, adding them together and taking the square root, we get 5.158. And actually they rounded to the 10,000, so 5.1583 would be the answer. So there we go. That's the force in pounds. And then we need to get this angle in here. So to get that, I'm going to take arc tangent of opposite, which is this blue value, over the red value, which is the adjacent. So we'll put that into Desmos now. And there we go. We get 75.8 degrees rounded to the nearest tenth. So we'll say 75.8 degrees from the horizontal. And I mean, really, I'd almost say this is negative because we're going out horizontal. We're coming down this way. But they have it in the back of the book as 75.8 just as is. So we can leave it like this. That's how you do it. Done. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.